And off we go. Okay, so here's where we were last time. We were talking about parameterizations. Let me just remind you the broad stroke of what a parameterization is. A parameterization gives position as a function of, I'm going to say time. Now again, it doesn't have to be time. You don't have to think of it as time, but it could be any single parameter. And in some cases, maybe something other than time makes sense. But I just, as a default kind of, getting started point of view, I think it's good to think of it as time. So position as a function of time. And I did the hand-waving argument last time that literally when you do like this with your fingertip, right, notice you are defining a position for every moment of time. So I argue that a parameterization is a function that draws a curve, right? I think that's a nice way to think about it. So, okay, so let's dive into an example. Let's see here. Here we go. So, this is a parameterization. Position, x comma y, which I like to abbreviate with just the vector x. Position, so x comma y. And notice the position given by its two coordinates is a function of time because those coordinates are functions of time. So that's a parameterization. Now, the natural next question that comes up is, okay, well, yeah, but what is this a parameterization of? What curve does this draw? Or we might say, what is the parametric curve described here? So, now how you identify the resulting parametric curve is not an algorithmic process. It is not a, here, just do this and that'll be the answer. This is a situation where there are various different tools that you can use that are convenient in various different circumstances. And so y'all are going to hear me refer to a particular metaphor throughout this course. I like to think of the various different techniques that you might use as being tools, and you're going to have a collection of these tools, and what do we call a collection of tools? Well, I like to think of them as being in a mental toolbox. So I'm going to show you several tools for your parametric curve toolbox. And here's the first one. The first tool is to notice that sometimes you'll just kind of recognize. You'll just, oh, hey, check it out. I've seen that formula before. And in particular, you notice that we have this convenient pre-existing relationship between cosine and sine. We just happen to already know that, right? I just, oh, hey, wow, just kind of notice that sine and cosine are related by the Pythagorean relation, and therefore every point on that parametric curve is on the curve described by this equation, which of course is the unit circle. So that is a parameterization of the unit circle. What do you think? Everybody on board? Everybody buys it? Okay. All right. We got lucky with this one. I happened to notice a convenient pre-existing relationship. Okay, so what if that is not the case? In other words, as in most of the time, what are we going to do? Because we, of course, most of the time won't just notice. So here's another method, another technique you can use. Here we have position as a function of time. Now, I did not explicitly write x comma y equals, but keep in mind, when you write an ordered pair representing a point in the xy plane, the first coordinate is x, the second coordinate is y. Right? So in what I'm going to call that first equation, you can solve for t, like so. You can then take what you solved for t in the first equation and plug that in for t in the second equation. And then that second equation, y equals 3t plus 4, turns into y equals 3x plus 7. And that is a good old, regular old, plain old equation. Nothing. This is not a parameterization anymore. There is no t, right? This is just an equation. It's the equation, of course, of a line. And so likewise, then I can conclude that that parameterization, wherever it came from, I don't know, but that parameterization traces out that line. Everybody good? So, different tool for different circumstances. Now, here's another way that you can address this same parameterization. This is a different tool for different circumstances. You will notice I'm starting here with our equation for x, and I'm going to observe that there's a when you look at this formula for x, here, let me highlight. Here's our formula for x, and here's our formula for y. Yeah, they're structurally similar. There's just constant plus multiple of t in both cases. They just happen to look a lot alike. And when you notice something like that, you can entertain trying the following. I'm going to take the expression for x and see if I can manipulate it around and turn it into our expression for y. And that ends up being pretty easy in this case. Right? All you got to do is take that t minus 1, just multiply by 3 and add 7. Not that much to it. Easy manipulations. Now, I've got to be honest about it. You got to do the same thing on the wrong color. You got to do the same thing on the other side of the equation here as well. And then notice what results. What results from this process is, again, an equation. Again, a familiar equation. Again, as it should be, the same equation that we got from the other method. So, different method for coming to the same conclusion. How we doing? Yes? Do you want me to repeat it? Okay. So the idea is to take this formula for x, do stuff to it, keeping, you got to be honest, of course, right? And try to turn it into a formula for y. And then the point is the relationship between the x and y results. Yeah. Okay. So, which should you do in which circumstance? Well, this kind of depends. Every situation's different. Roughly speaking, try to use the right tool for the right job. If you need to put a screw into a board, don't use a hammer. Right? So you want to look at the circumstance, see what do you have available to you, what do you notice that's convenient, what parts of which of these tools is going to be easy, what's going to not be easy. And I'll point out that we got lucky with this first one. This process of solving for t happened to be easy there. What if that formula for x, t minus 1, what if that had been t cubed plus 4t minus 7? Right? Some cubic expression. That's going to be really hard to solve for t. And then this method here becomes not very attractive. Right? See what I'm saying? Right. On the other hand, what if these two expressions here were unrecognizably related? Just nothing apparent, no clear way to sort of turn one into the other. Well, then this method probably wouldn't work too well. So, again, let the context be your guide. And again, this is tools for your toolbox. Okay. Here's another method. We're going to address a three-dimensional scenario. Now, this is a three-dimensional example because you'll notice this curve, position as a function of time, 3 coordinates. That means we're in 3 space. Okay, well, let's see here. I guess I could try to find an algebraic relationship between x, y, and z, and in some cases you can sort of do that, but if you take it as your goal to find an equation here, you're kind of out. It's not a promising strategy to try to find an equation. Because if you think about it, a single equation would typically create a surface in 3 space. We know this is a curve. Position is given as a single function of a single variable time. We know we're tracing out a curve, not a surface. So I don't think it's likely that we're going to find just an equation. Not that it can't be done, but in this case, it's really, really hard. Okay. So here's what I'm going to do instead. I'm going to just kind of notice that if I were to just think only about the projection into the XY plane, if I were to just imagine taking everything on this entire space and just smushing it down into the XY plane, kind of throwing away the Z coordinate. Well, then I would only have the X and Y coordinates remaining. And what do I know about those X and Y coordinates? Oh, I recognize those X and Y coordinates. We've seen that example before. By the way, that's a standard example. We're going to see that explicit parameterization a bunch of times in this class, right? So we get lucky, as we often will, and sure enough, I know what that projection is in the XY plane. Looking at the shadow in the XY plane, we've got a circle. And then you can make an analogous argument. What if you think about just the Z coordinate? So again, geometrically that says we're throwing away X and Y. It's like we're squeezing all of space down into just the Z axis. Right, okay, which means we're only looking at the Z coordinate. And what can we say about just that Z coordinate? Well, it's a pretty simple formula. Z is just T, and that means that we're just going at a constant, we're rising at a constant sort of vertical rate. So now you put this together, we're looking for a curve whose shadow in the XY plane is doing this, and whose altitude is doing that. And you kind of combine these observations, and all together that is doing this move right here, namely it's a helix. That's just how this one happens to work out. How are we doing? Yeah?
How do you know that it's a circle projection on the XY plane just from a cosine?
Yeah, just because that cosine T, sine T thing is literally exactly what I've already studied, and I just kind of remember that example. Does that make sense? You okay?
Yeah.
Oh, okay. Okay. Yeah.
Why is it doing like an helix and not like a cylinder?
Do what now?
Why is it doing a helix but not like a cylinder?
Yeah. Okay, right. So, because this is position as a function of time, right? So at any given moment in time, we have a single point, and as time passes, we get different points. And if you have position as a function of time, it traces out a curve. Okay. It doesn't trace out a surface.
Okay.
Is that satisfying?
Yeah.
Yeah. Okay. Let me go to her back here.
I'm so confused why T is just going up. Like, how do you know T is going up and it's not going like this way?
Oh, well, yeah, because this is literally the Z coordinate.
Okay.
Yeah. So I'm not saying. Notice we're not literally going exactly straight up, right? But this T is a reference to the Z coordinate, and it's just telling me what my altitude is as a function of time. Okay. So where in this plane I am at a moment in time, that I don't know, but I know that it's rising. Yeah, right. And did you have another?
Yeah. How do you know the direction of the spiral?
Oh, yeah, that's a good question. So if we come back to here, I'm going to say you can just kind of plug in a few points. Right? Plug in T equals 0, you know exactly where you are on this curve. Plug in a little slightly larger value of T, just kind of start plotting points, and you'll notice that this is counterclockwise.
Okay.
Yeah. And we'll have some other methods that we'll talk about later on that'll address that same question. Yeah.
Is writing the XYZ like separated comma, like the comma for
also fine.
Is that just all like?
Yeah, it's just X comma Y. Yeah, comma means new line. It's sort of a typographical shorthand, right? So X comma Y is just a shorthand for X and then new line Y. Yeah. Okay. So different techniques for different circumstances, tools for your toolbox. You got to kind of familiarize yourself with the tools, and then you can learn how to build things. Okay. Moving along. What if we need to go the other direction? So you'll notice all the examples I've given you so far, we started off with a parameterization. And then the question was, what's the corresponding curve? Well, very often in the real world, you start off with some sort of knowledge of the curve, but you want to create the parameterization. So this is called parametrizing a curve. So how do we parameterize a curve? And again, tools for your toolbox. There is no single algorithmic way to do this. This is not a plug and chug. This is there's various different techniques and etc. Okay. I'm going to start with my favorite. It's what I like to call the graph parameterization. This is a fantastic method. It doesn't apply all the time, but when it does, it's super easy. Super easy. So the catch is that it only applies to graphs. Namely, you have to have solved for one of the variables in terms of the other. You can't always do that. Right? So, for example, you look back to here. This curve right here, I cannot solve for one of the variables as a function of the other because there'd be multiple values, and that's not what a function is. Right? So, not all curves are graphs, but some curves are graphs. And when they are, here's the simple method. It's so easy. The simple method. Whatever is the input variable to that function, in this case x, just let that equal to t. That's all it is. Identify which variable is a function of the other. That other is the input. Call it t. Celebrate. So let's see how that works down here. Now we'll start off by noticing that in fact, yes, y is a function of x. This is therefore a graph. The input variable is x. We let x equal to t as instructed there. And I claim it's all over with the shouting. Because, after all, if x is t, then I kind of have to let y be t squared. And position as a function of time. Everybody see how that works? It's very plug and chug. Now again, it doesn't always work. It only works if it's a graph, and there are other methods, and this won't always, so all the disclaimers, but when it works, it is easy to do. Okay. All right, let's see another example. Let's see here. I gotta let me just erase all of that. Okay, let's look at this equation right here. Is that written in the form of one of the variables as a function of the other? Well, no, it's not. Okay, well, let's see. Can I solve for y in this equation? Not really, right? It's we got y in the exponential and outside of the exponential. That's a losing deal. You can't solve for y there. It's tempting to throw up your hands. But conveniently, there's no law that says it has to be y that you solve for, as long as you can solve for one of the variables in terms of the other. So I could totally solve for x. No problem. And following the above rule. The above rule says let t be the input variable. My input variable here is y. So as advised, I'm going to let that input variable y be t. Basically all over with the shouting at this point, because I can take this and plug it into there, which pretty much forces x to be that expression. Again, game over. I have position as a function of t. Everybody good? Okay. Real slick move. When you have a graph, let t be the input variable. Okay, now there are other circumstances. This is a really cool example here. It is also detail heavy example. So I'm going to, in the interest of time, again, tough choices, I hate having to do it, but I'm going to hit what I consider to be the important points on this, and then I'm going to leave you all to read through the details. And this is a fantastic exercise to make sure you understand and follow not only where did everything here come from, but what was the thought behind doing it that way. right? So, okay, so let's talk about the big picture. What the question is asking here is that we have a wheel, imagine like a bicycle wheel, and there is a reflector at the end of the bicycle wheel, where they often put the reflector, right? And now as the wheel rolls along the x-axis here, you kind of imagine it rolling kind of like that, right? And where the reflector had been, where my thumb is, right, over as it rolls, eventually the reflector is up here, and you can kind of see that the reflector is going to trace out, there's the reflector, it's going to kind of trace out a curve that'll sort of do about like that. And I think y'all have probably seen this in the real world, right? And it's dusk or something outside, the street lights are on, somebody's riding by on a bicycle, and that reflector does this real kind of jerky, lumpy motion like that. We all seen that? So that's the curve that we're going to parameterize here. Interestingly, if you try to write an equation for this curve, crash and burn. It's really hard. Basically doesn't work. If you try to write this as a graph of some function, crash and burn. Does not work well. But we're going to be able to parameterize it without too terribly much trouble. Okay, so now let's talk about the big points. The first big point is to be very explicit about what your parameter is. A lot of times when I see students trying to solve problems like this, they're writing down a bunch of stuff, but they never really quite get around to deciding and unambiguously indicating what is their parameter. Where's T? What in the picture is your T? So make sure to do that. Now, the choice that I've made here is to, let's see here, let me get my colors in order here. So there's our reflector at the start, and here's where the reflector is a bit later. And what we're going to do is we're going to drop a vertical from the axle, right? And notice that we start with the reflector on that sort of straight down vertical. And then we're going to notice that as the wheel turns, this angle here, measured counterclockwise from the vertical, ending at the spoke that has the reflector on it, that angle we're going to call T. Why did I pick that parameter? There's a bunch of different choices that you could make. Some people like to use the sort of the polar coordinate theta. There's a point of view there. There's pros and cons. I like this T because when the problem begins, T is 0. That's nice, right? And then as the wheel rolls, T, measured clockwise, as I've indicated here, increases as time should. Okay? It gets a little counterintuitive. If you ever set up your parameters so that T is decreasing, it ends up feeling very sci-fi. You're moving backwards in time, and it just gets creepy. Right? So I like it like this, but you have other options. Okay, notice though, I made a decision, and also I have clearly indicated that decision on my diagram. And that's a big deal. Okay, second big point that I want to get to is that vector algebra is going to be our friend in this. This is a really powerful point. Vector algebra. So again, keep in mind, we're trying to understand, let me do better graphics here. We're trying to understand this point. I want a formula for that orange point P as a function of T. And I'm going to make this observation that, look, that is the sum of this point where the axle is plus this vector representing the spoke that the reflector is on. So blue plus green, and let me zoom so we can see better here. If it'll cooperate. There we go. Okay, blue plus green equals orange. Yeah? All right, so what's nice about this is blue and orange are actually pretty easy to write down. I mean, if you think about it, the axle, what I have colored in blue there, it's just going in a straight line. That's pretty easy to describe. Listen, details to be worked out, but it's a straight line. That's not that bad. And if you think about this green vector, what are we going to say about that green vector? Well, it's easy to get this a little wrong. There's a temptation to say, ooh, that green vector is kind of doing like this, that it's moving while it's rotating. But remember, it's a vector. Vectors do not have a location. Vectors are just direction and magnitude. That's it. So that green vector is like this. That green vector is just going around in a circle. And that's not that bad to describe either. Is everybody with me on that? So, wonderful observation. Sometimes, this being a great example, where am I now? Sometimes a very complicated to describe thing is the sum of two much simpler things. There is no conservation of inconvenience. Right? We've reduced our inconvenience quite a bit by breaking orange down into green and blue. Okay, everybody's happy with that. The last big idea in this that I want to make sure to talk about is what I have here in the middle of the page here, and that is the x-coordinate of our axle. Here's our axle in blue. The x-coordinate of our axle is this distance right here. That's the x-coordinate. By the way, the y-coordinate's super easy. The y-coordinate is constant. Right? Otherwise, you'd have a really bumpy bicycle ride, right? So the the y-coordinate is just constant. But what is the x-coordinate? And there's a physical observation here that is very key. The physical observation is, if you think about it, this x-coordinate of that axle is the amount of road that has touched rubber. And I make a physical appeal that the amount of road that has touched rubber has to equal to the amount of rubber that has touched road. Physical appeal. Road equals rubber. Everybody buy that? Otherwise, the wheel would be slipping and sliding and skidding or something like that. So who cares? Well, we care because you look at where t is, right? T is this angle right here, and we've already decided that's our parameter. Well, this green distance, the amount of rubber that has touched road, is going to be easy to write down because that's just the arc of a circle of a known radius and a known angle. That's easy geometry. And that arc being the same as this x-coordinate gives us what we need. All right. So there are some more details to be put together. I want you all to pay careful attention when you're looking through these details to think through that we actually have two different angles to think about down here. Right? There's the angle that I've already called t, and then there's the classical polar coordinate angle theta. They're not the same. They're not interchangeable, but they are easily related to each other. And so you want to keep that in mind, and then you can write down some equations for d in terms of theta, and then relate theta to t and plug them in. And don't forget your angle addition formulas that allow you to convert this stuff down to here. Okay, so details for y'all to think through. I think it's a healthy exercise. Okay. All right. Moving along. Okay, how do we parameterize a line? Well, which line? Okay, so if I'm going to ask you to parameterize a line, I have to be clear which line are we talking about, and how am I going to describe the line in the first place? Well, I'm going to give you a point on the line. That doesn't do it. That's not sufficient. If I say, hey, I'm talking about the line that goes through that point. Well, yeah, but there's a lot of lines that go through that point. That's not enough information. But if I say the line that goes through that point and is parallel to that given vector, now we have a fully characterized line. There is only one line that goes through that point and is parallel to that vector. Everybody happy so far? Okay. Okay, so given those specifics, how do I parameterize this line? And the clever observation here, again, we use vector algebra. If I have some other point on this line, calling it x, then notice x minus x naught is parallel to v. And if it's parallel to v, v being non-zero, then that means it's a scalar multiple of v. I'm going to let that scalar be t. Why not? I get to define t however I want. That's how I choose to define it. And the result then is very convenient, that x is x naught plus tv, namely t times the given vector v. And so there's your parameterization position as a function of time. Nice little slip. Everybody happy?
Could you explain one more time?
Okay, which part?
This part.
Okay, yeah. So the idea is that this, what I have in green here, is x minus x naught, right? And so another way to say that is x is x naught plus this green vector. Yeah. Is that cool? Yeah.
If you were to show that, like, as you have shown, like, let me pull it up. Like you have shown right here, how would you do it?
Oh, well, yeah. So that's written in terms of coordinates, and I didn't write any of this. If you have coordinates for x naught,
okay,
and maybe it's x naught comma y naught, something like that. And if your v might be like a comma b or something, well, now you have coordinates, and then you can just plug in coordinates. Yeah.
Okay.
But for whatever it's worth, I mean, there is a temptation to want to write everything in terms of coordinates. Coordinates serve a purpose in some cases, but I think there's a tendency to use coordinates too much. Vectors are actually wonderful things. Vectors are geometrically natural, right? Coordinates are kind of an odd. I mean, they serve a purpose in certain cases, and our calculators are really good at working with scalars, and coordinates are scalars, and that's nice. But really, there's no particular reason to want to write this in terms of coordinates, unless you really sort of need to for some specific reason. Yeah.
This is like a clarification. T is a constant, right?
T is a scalar.
Oh, because it's scaling the parallel vector.
Yeah. So t, I use t to be my parameter. I always like to at least eventually think of t as being time. And so in this case, yeah, if I think of t as time, then at t equals 0, we're here. And at t equals 1, we'd be about, about here. T equals 2, we'd be about there, etc. And so it's tracing out this line. Yeah.
And they could be like anywhere in space.
Do what now?
Could they be like anywhere in space?
I don't know what they...
Since they're vectors, like could v and the x that we just solved.
Well, v doesn't have a location, but x naught does.
Okay.
X naught's a point, yeah. So this traces out literally exactly that line, yeah. I can draw the v kind of wherever, but yeah, v is just a direction and a magnitude. Yeah. Okay. Last question. Yeah.
Can I still have a quick question of that bicycle question?
Okay, if it's real quick.
Yeah. So
What?
that
Yeah.
ATA thing.
Yeah.
That particular vector. Why do I feel like is talking about D rather than A? Because D is constant on the y direction, right?
So you're talking about this right here.
Yes.
Yeah, so A, you got to keep in mind, this second coordinate here being A is saying that we're always at that altitude, which is like so, right? And AT, remember, keep in mind, was a reference to that distance, which gives me that coordinate there. And so between the two of these, that identifies that point right there. So this might be a good after-class question, office hours question, something like that. Is that cool?
Yeah.
Okay. All right. So let's see here. Now I gotta get back to this. Oh gosh. Yeah. Here we go. Okay. All right. Is everybody good with the line? Yeah. Okay. All right. Here's another tool for your toolbox. Sometimes what you need is a tweak away from something you already have. So, just a quick reminder, we've already discussed how to parameterize a circle. Right? We've seen that one before. We've made uses of that parameterization a couple times already. That's our circle C. And now we are being asked, it seems, to parameterize this ellipse that has this equation here. And y'all remember your high school algebra, right? This ellipse is centered at the origin, and the sort of the x radius is 3, and the y radius is 2. So it's kind of like that. Okay. So how do I parameterize the ellipse? So big idea is, look, the ellipse is a lot like the circle. It's not the same. But ellipses come from circles, arguably. All right? Ellipses are what you get when you deform, when you stretch a circle by appropriate amounts in the two given directions. So, I can just see right here from this picture, this circle has radius 1. This ellipse, at least in the x direction, has radius 3. I need to stretch it by a factor of 3 in the x direction. And the way I'm going to do that is by taking my existing parameterization. I'm going to stretch it by a factor of 3 in the x direction by just literally multiplying my x coordinates by 3. And that stretches as it's supposed to. Likewise, you can see I'm going to need to stretch by a factor of 2 in the y direction. How do I stretch by a factor of 2 in the y direction? Well, multiply those y coordinates by 2. And there you go. And this is a parameterization of our ellipse. Does everybody buy it? Okay, now you may be a little concerned. I made this assertion that ellipses are not only approximately what you get when you stretch out a circle, but I'm claiming that an ellipse is exactly what you get when you stretch out a circle. And if you're a little suspicious that maybe that was presuming a little too much, maybe you're not sure that you believe this result, let me point out that this is easily double-checked because I can just take this parameterization that I've concluded, right, and I can just plug it in, and sure enough, it works. So every point on this parameterization satisfies that equation, and therefore, this is a parameterization of that ellipse. Everybody good? All right. Okay, now here's a kind of a philosophical point. A lot of people make a mistake. I blame high schools by being a little too sloppy in how they think about relationships between algebra and geometry. And I was probably guilty of this myself when I was, sufficiently young age. A lot of people are accustomed to the idea that what an equation is it's just algebra that you write down and then it describes the curve. Period. But here's the thing, a parameterization that we've just created, if you think about it, is algebra that we write down that describes a curve, right? So we have two different kinds now of algebra that we write down that describes a curve. So what's the difference? And the answer is there's a huge difference, tremendous difference between equations and parameterizations. And here's one way to think about it. I like to point out that a parameterization is a point generator, because a parameterization takes some input value of t and literally produces a point on the curve. It is quite literally generating points on the curve. So point generator. Is this what equations do? Not even close. Equations just don't do that at all. Equations, kind of the opposite. Equations take a point that either is or isn't on the curve, we're not sure. That you plug into the equation, and then either the equation works or it doesn't. If the equation works, then it's on the curve. If the equation doesn't work, it's not on the curve. So that's what a test is, right? We take points and we plug them in and get either a yay or a nay. We are testing those points. So I think it's really important to keep this in mind. Yes, they're both algebra. Yes, they both describe a curve. But they do so in these really different ways. Does that make sense to everybody? Okay, so here's a great example of how we can capitalize on this observation. We'll look at this example here, and I'm fairly sure I recall that there's at least one homework exercise that's kind of along these lines. What's the intersection of this parametric curve with that plane? Just looking for the points that are on both. Okay, well, we got to have a strategy here, right? What could be our strategy for how we're going to identify such points? And here's what I propose. Keep in mind that a parameterization is a point generator. So out come points by way of those formulas. You give me a t, out comes x, y, and z. Now, that's generating points. And what I'm going to do then is, having generated points that are on the line, I'm then going to test exactly those points and see if they're on the plane. And here's how we test those points. I take these points, I plug them into this equation, which becomes this, and then I ask, did it work? Right? For what values of t does this work? So we are literally testing points that we've generated. That make sense to everybody? All right, now do keep in mind when I say, plug in, let's see here. So there's our x, and so I just take that formula and put it where the x is, and there's our y, and so wherever the y was, I put that formula. And here's what our z is, and so wherever the z is, I put that formula. And so the resulting algebra is pretty doable. Right, we get this equation, which turns into that, which turns into this, and I have solved. We're almost done. I have now the allowable values of t, but let's not, spike the ball on the 2-yard line. The question didn't ask us for values of t. The question asked us for what are the points, right? So I do need to now ask, what are the points themselves? And so you take the t's that you've just solved for and you plug in to the parameterization and solve for x, y, and z. And those are the points. Everybody get it? Everybody happy? Yeah.
Why do you say on the plane with instead of intersects with a line or something?
So first of all, this is a plane, not a line. And we're going to study planes more later. I'm kind of assuming that's. A lot of this kind of stuff should have been covered in 218. I know maybe it wasn't. And I know it was may have been a while ago. But yeah, so this is a plane. We'll see more about that later. A line in space does not have a single equation like that. And I could say what is the intersection of this curve with that plane. Or I could say which of the points on this curve are on this plane. Yeah, there's different phrasings, but they all mean kind of the same thing. Okay. Yep.
And solving that gives the only solutions.
Yeah, that's right. That's right. Because we've literally taken all the points that are on the curve and we have tested them. And if it's going to work, it's going to have to. Yeah, right. Okay. All right, so let's talk now about lines in space. And as I just said, we don't have an equation for lines in space. It's just not a thing. Okay, I can't have an equation. So if I want a point tester, which is the role that an equation would have played, I can't have an equation. But is there some other sort of a point tester that I can have? And here's how that works. It's a clever argument. But what we're going to do is start off with a kind of silly, pointless observation, seemingly, and then we're going to kind of rephrase it and realize that it's exactly what we need. So if you come to me with a point and you want me to test whether this point is on a parametric line, one way to test it, I suppose, this sounds sassy, but one way to test it would be to just ask, hey, if there is some value of t that generates that point. Well, yeah, of course, right? That's what a parameterization is, right? If a point is on the line, then there is some value of t that generates that point. Okay, useless, so it seems, because I've been told that I should look to see if there is some value of t, but I haven't been given any advice on how to go about deciding if there is some value of t. How would I decide if there is such a value of t? So the slick move is to realize that you can take this vector equation and rewrite it as these three scalar equations. And the idea is that what we really have here is three separate scalar equations in this vector equation, in each of which I can solve for t, and when you solve for t in those equations, you get these three equations. Just solving for t in each of the three coordinate equations. Okay, now we have a different question. Let's look at this second line here. Does there exist a value of t that makes all three of these equations work? Okay, here's a silly example, deliberately silly. Is there a value of t that is equal to 2 and 3 and 7? Can y'all think of any value of t that's equal to 2 and 3 and 7? No, it's silly. We're deliberately silly, right? Okay, all right. How about this? Is there a value of t that is equal to 2 and 2 and 7? No, right? Right? Being deliberately silly. There's only one way that there could possibly be a value of t that's equal to all three of these things, and that is if all three of these things are equal to each other. And then, yes, there is a value of t that's equal to all three of these things. It's whatever that value is that all three of these things are equal to. That's t. Okay. So this is what we call the symmetric equations for a line. And you will notice the plural, very important. This is not singular. This is two equations, isn't it? And you need the two equations. And between the two of them, that is a point tester. Whatever point you give me, you can just plug in the x, the y, and the z. You compute these three expressions. You see if all three of these expressions are all identical. If they are, cool, yes, that's a point on your line. Yes.
Real quick question.
Please.
What is the third looking t?
Third.
Your left-hand side?
Oh, yeah. Okay, I'm sorry. Yeah, I always forget to explain this notation. You're talking about this thing right there?
Yeah.
Yeah, sorry. Okay, so let's see here. So let me explain all of this notation. This weird-looking backwards E is a little mathematician shorthand, and that means there exists or there is. And this little oddball means such that or so that. Yeah. It's just a little shorthand for convenience. Yeah. Good question. Yeah. Okay. Let's see here. All right. So very quick, super quickly. So we are done with 1.2 now. I just want to remind y'all that there's a lot in this section here that's review. So I'm going to go super quick through all this stuff, by which I mean on Friday because we're kind of out of time now. But just make sure that you remember dot product. It has many properties. I'm going to assume you're good with those properties. Remember, it's the model for inner products. So it is kind of a big deal, and we'll pick up there next time. All right, y'all have a good rest of your day. See ya. Give me 2 seconds. 2 seconds.